All right, so we're going to start week 6 today. Week 6 talks about the T distribution as kind of the main concept, but we're also going to talk a little bit about confidence intervals and interval predictions, interval estimates, and then we're going to apply that T distribution that we had to hypothesis testing going forward. So when we're dealing with confidence intervals, the concept here is that when you go out and you estimate something using the mean, right? So if I want to say I'm going to estimate the average height of all people in Nevada, and I'm going to use our class as an example, I'm going to take the average height and see how it does. So I'm trying to predict the population mean for height. And the only thing I have when I do that is the sample mean, which is x bar. That's called a point estimate. And the problem with point estimates is that they are almost 100% wrong. You are almost never going to have the exact answer going forward. So the concept is that instead of giving a point estimate, we can create an interval estimate to help us have a better chance of accurately predicting what that mean value is. So, interval estimate, interval or range of values used to estimate a population parameter. Level of confidence, right? So we don't just swag these things. That's probably one thing I can talk about in this class when it comes to our discussion posts, when it comes to mathematics and statistics in general, right? I read a lot of discussion posts that say, I think, I believe, in my opinion. No, none of that stuff ever needs to happen in math and statistics. All right, you should know the answer. You should say, this is the answer, not I think that this is, you shouldn't say, I think this is a statistic. You should say, this is a statistic. We want to make sure we sound like we know what we're talking about. Anytime you start saying, I think, I feel, that just goes to show that you don't know the answer, right? We want to get to a point where we know the answer. So we don't want to do any swags. We don't want to do anything like that. What we want to take a look at is go, okay, so I have a point estimate, X bar. I'm going to create some level of confidence in my answer. It could be 90%, it could be 95%. It can be whatever I want it to be. We'll learn how to deal with that here in just a little bit. And then we use that information to create a confidence interval. So let's talk a little bit about this. So we have our confidence interval. Where does that confidence level lead us so that way we can make some kind of interval estimate? So far we've talked about the Z distribution. The confidence that I'm talking about comes from the normal distribution, and it'll look like this. So to find a critical Z value, which we'll need to create a confidence interval, we need to understand that the normal distribution is symmetric and that the area between my critical positive and negative critical Z values needs to be my level of confidence C. So if I want to make a 95% confidence interval, then the area between these two values needs to be 0.95. I want to create an 80% confidence interval, that area between needs to be 0.8. So that's the concept of how we get it. So how do we actually find this in practice? So here's what we do. In order to find the critical Z value, we take the level of confidence in area, not percentage, subtract it from 1, divide it by 2, and then find the corresponding Z value using the Z table or some other tool. So let's take a look here. 90% confidence level. Area between is 0.9. Subtract that from 1. That gives me 0.1. Then I divide it by 2. Gives me 0.05. Now I find the z-value that corresponds to an area of 0.05. We open up our z-value here. Look for 0.05. Falls somewhere in between these two. Looks like almost directly in between these two. I got negative 1.64. So it's somewhere between negative 1.64 and negative 1.65. So we're going to say that it is negative 1.645. So my critical z-value is always positive, and I'll explain that in a minute. We don't worry about the negative aspect, but I'm worried about that number 1.645. So my critical z-value would be 1.645. 85% confidence level. 0.85 is the area between. Subtract that from 1. That gives me 0.15. Divided by 2. That gives me 0.075. Come back to my table. Find 0.075. Looks like right about here, 0.07493. That's pretty close. And that's as close as I'm going to get. Negative 1.44. So my critical value will be 1.4. Questions? All right, walk me through 92. How do I find 92?
It'll be 0.92.
Okay.
Minus 1, and then divided by 2.
Okay, what's that give me?
0.04. What, negative 0.04?
It's just 0.04.
Okay.
Yeah, we gotta be careful, right? We take 1 minus the area.
Okay, got it.
Yep. So okay, so we have 0.04. Now, tell me where that is on this chart. Let's scroll up so you can see the top.
It'll be between 0.04006 and 0.03.
So you've got this one down here. I see what you're saying. So which z value, and we're going to use the 0.04006 because that's pretty close. So what is that z value?
1.75.
That's it. We're going to leave it with that.
Just that one, okay.
Yep. 1.75, because if we were to approximate it, it would actually be like 1.75, maybe like 1.7505. We can only do as good as we can with the tape. So, but good job, it's 1.75. 1.75 is my critical Z value.
And I have a question as well.
Mm-hmm.
Sometimes I will confuse myself, like when I get the answer, like the one that we just got, the 0.04. I would go over to the Z value to look at 0.0, and then I'll go over to 4 and get that.
Mm-hmm.
How can I, know which one to do at a certain moment?
That's a good question. That's a good question. So, in general, if I have a Z value, then I'm looking up the numbers on the left and finding the area under the curve. So if they give me a Z value, I use the Z value to give me an area under the curve. In a situation like this, I'm just working backwards. I'm giving you an area under the curve, and I need that to find a Z value. So if we come over here, right, everything inside is an area under the curve that corresponds to Z values, but is not a Z value.
Hmm.
So if I am ever given an area, a probability, then I'm going to use that information to find a z-value. So I'm going to use the middle of the table to help me find a z. If I'm given a z-value, or if I compute a z-value and I want to find the area under the curve, then I come and use these values out here on the side.
Got it.
All right. Last one, 95% confidence interval. What do I do with this one?
It turned into 0.95.
Okay.
We have 1 minus 0.95 will get you 0.05. Divide that by 2, which is 0.025.
Okay.
Looks like that will be around 0.02500.
It's almost perfect, right? So what is that z-value?
1.96.
1.96.
Mm-hmm.
Good. So our z critical here is 1.96.
You wouldn't put the negative, you would just leave it like a positive?
And I'll show you why here in just a minute.
Okay.
Yep. All right. So that's how we go about finding them for the z distribution. And one of the interesting things about z distribution is, if you recall, we make it, we transformed our normal distribution into a z distribution because it keeps things constant all the time for us. It has a mean of 0, standard deviation of 1, and it stays constant. So we can use these types of tables. So because of that, the critical z values that I get never change based on my confidence. So I create a confidence level, it will have the same critical z value regardless of anything else. So critical z values, if I have an 80% confidence level, my critical z value is 1.28. 90% confidence, z critical is 1.645. 95%, we just found that one, z critical is 1.96. 99%, 2.576. It is very common that we see 90 and 95% confidence intervals. Every now and then you see 99% confidence intervals. I have seen down to 80%, but usually 90, 95 tends to be the standard confidence interval. So here's how this goes about creating a confidence interval. So I take the level of confidence I have, and then I find that critical z value. I'm then going to take that critical z value, multiply it by the standard error, sigma over the square root of n, and that's going to give me what's known as my margin of error in my estimate. So my margin of error E is equal to z critical times the standard error, or z critical times sigma over the square root of n. So I take, in order to find my confidence interval, I'm going to take my test statistic that I'm taking a look at, which in this case is going to be my mean x bar. And then I add the margin of error to it, and I subtract the margin of error to it, and it's going to give me a confidence interval. So a C confidence interval for the population mean mu is as follows. X bar minus E is less than mu, is less than X bar plus E. So that is how we go about computing a confidence interval. So when we write the confidence interval, it's going to look a little something more like this. I'm going to have my X bar minus E, comma, my X bar plus E, and they're going to be in parentheses. That's going to give me my interval estimate. Questions? All right, so that talks about interval estimates. We'll talk about it a little bit more coming up too. So we're going to segue into what we call the T distribution coming up. So we've learned about the normal distribution, how it acts, what it is, how to find those probabilities. But now we're going to talk about the T distribution. So if we have a normally or approximately normal distribution, and we do not know the population standard deviation, we're going to use the T distribution. So the T distribution is a family of curves. We'll see that in just a little bit. But it was called the student's T distribution, and it's very similar in form to the normal distribution. And as my sample size approaches infinity, it actually goes and becomes the normal distribution. So this was invented by a guy named William Seeley Gossett. So I'll tell you a little story about this for those of you that are still awake. William Seeley Gossett was a guy who worked for Guinness back in the day. And so Guinness obviously made some beer that everybody liked, and they were trying to find a way to become more profitable by taking a look at their hops and assessing the resins within the hops. And so the problem is that, you know, they had to sample so many of their hops to see if they were getting the right ones for their beer, that that they were wasting a lot of product. So William Seeley Gossett came out with a way to estimate the error in their measurements at smaller sample sizes. And then when he did all that math, he created what we know today as the T distribution. So the problem is that Guinness didn't want to let this get out. They were like, well, we just found a way to analyze our data in a much better fashion than our competitors. We don't want to let them know what we're doing. But William Seeley Gossett, being the great person that he was, said, hey, this is breakthrough. This is important. We need to share this. So he worked a deal with Guinness where he could report it as the student's T distribution and publish that paper, not showing that it had anything to do with Guinness beer. So William Seeley Gossett created the student's T distribution. So anyway, student's T distribution, if the distribution of a random variable x is approximately normal, then T equal to x bar minus mu over s over the square root of n follows a T distribution. So the T distribution and the Z distribution look almost identical. The difference is in the T distribution, we don't know sigma, right? We don't know the population standard deviation, so we estimate it with the sample standard deviation. So let's talk about T distribution, some of the properties of the T distribution. The mean, median, and mode are equal to 0, so it's very similar to the Z distribution. It's bell-shaped and symmetric about the mean. Total area under the curve is equal to 1. Now, some of the differences. The tails in the T distribution are a little thicker than those in the normal distribution. Standard deviation of the T distribution is going to vary with sample size, but it's greater than 1. And the T distribution is a family of curves, and it's a family of curves based on what we call the degrees of freedom. So instead of getting into detail about what degrees of freedom represent, when we're dealing with a T distribution, estimating the population mean, the degrees of freedom are equal to n minus 1. So df will be n minus 1, where n is my sample size. As the degrees of freedom increase, the t-distribution approaches the normal distribution. And so we talked a little bit about that n being greater than or equal to 30 rule. If my sample size is greater than 30, this is where that comes from. So what do these curves look like? So this is t-distribution curves. Like I said, it's a family of curves, and it depends on your sample size. So as we see, when n equals 2, I've got this light blue line here. It's got a small peak, and it's got heavier tails. The red, all the way up here, if you can see it, that is the normal distribution. So as we see, as n equals 2, that's what my curve looks like. As n equals 3, my curve looks like that. As n equals 6, it looks like that. And then when n is equal to 30, it's almost at that normal distribution, but not quite. Peaks a little bit lower, tails are a little bit heavier. Not quite there, but we're very close. And that's where that n equals 30 rule tends to come. So that is what that looks like, series of curves. And the reason why we have a series of curves depending upon sample size is because we are estimating the sample standard deviation, the population standard deviation using the sample standard deviation. And so there's error in that approximation, which gives us error that we need to account for at smaller sample sizes. So how do we find critical values and probabilities? We have a table that helps us with this. And a lot of times we're not overly concerned about computing the probabilities, although if we get a problem like that, I'll show you how we would do it. Usually what we do with the t-distribution is try and find those critical values that we just talked about a little bit. So on my left-hand side here, zoom in even more, this little V-looking thing, that's a Greek letter nu, that is my degrees of freedom. Degrees of freedom, n minus 1. So if I have a sample size of 10, then I would have 9 degrees of freedom, and I would come down here to the 9 row. And then these would be my t values that I would see in the chart. Up at the top, I have these alpha value here. That's that same alpha value that we think about when we're dealing with hypothesis tests. And in fact, if we take a look at this little picture up here to the top right, that alpha says this is the area to the right. So if I want my area to the right to be 0.1, I use this first column, 0.05, second column, 0.025, third column, et cetera, et cetera. All right. So one of the important things we need to know is when should we use the t-distribution versus using the z-distribution. Here are the key things we need to know. We should use the t-distribution when sigma is unknown and s is the only measure of standard deviation that we have. We are doing inferential analysis of the mean, which means we're looking at confidence intervals or hypothesis testing. Our sample was collected using random sampling techniques. Our data set comes from a distribution that is approximately normal. This is important. We need to make sure it's approximately normal. We need to make sure that it does not contain any outliers. That is also very important, right? We learned earlier in class that outliers can really impact the prediction of mean and standard deviation, which could really go about influencing our results and give us a lot of error in our assessment. And a lot of times we use it when the sample size is small. You'll learn that in class. Well, if n's not greater than 30, we use the t-distribution. If it's greater than 30, we use the z-distribution. That's not exactly correct, but it is often used in smaller sample sizes because we can't do that. But the reason why we use it in general is because we don't know sigma. That's the reason why we use it, because we don't know what the population standard deviation is. So I remember one day I was sitting in class with Dr. Navidi, and Dr. Navidi, he was the balls and the urns guy. So we're sitting in class one day and we're kind of learning about this. And he's like, oh, well, you know, he's spouting out this same stuff that I'm spouting out to you now. Oh, well, you know, if we know sigma, then we're going to use the z-distribution. And if we don't know it, then we use the t-distribution. So I raised my hand and I said, Dr. Navidi, when are we ever going to know sigma? Right? When are you ever going to know what the population standard deviation is? Whenever you're collecting data, you don't know what it is. Otherwise, if you knew what it was, if you knew what the population standard deviation was, you'd know what the population mean is, and there would be no reason for you to do the analysis. So he goes, well, Chris, let me tell you, Chris, because sometimes someone's been working there for a long time and they just know. That was the answer. That was the answer I got. Sometimes someone just knows what it is, and you use it. So in general, when I do statistics for a living, we almost always use the t-distribution. When we teach math classes and stats classes, we love to teach the z-distribution because it's easy, it's one thing, and it works for a lot. So anyway, things I want you to know. We use the t-distribution when we do not know sigma. When our data set's approximately normal and we don't have any outliers, often used when the sample size is small, but can also be used when the sample size is big. Questions? All right. So let's talk about constructing confidence intervals. So we talked a little bit about them with the z-distribution and kind of said, here's what a confidence interval is. Here's what it represents. Here is how we deal with them with the t-distribution. So if I want to create a confidence interval for the population mean using the t-distribution, which means some of the other things are coming up, such as we need to verify that we do not know sigma, and that S is our only assumption there. My sample is random. The population is approximately normal. And I'm going to put a note here that it's often intended for smaller sample sizes, but it could be used pretty much any time, and it should be used anytime we don't know sigma. All right, then we find our sample statistics, N, sample size, X bar, sample mean, S, standard deviation. We identify the degrees of freedom, N minus 1, sample size minus 1, the level of confidence we're looking at, and then we're going to find the critical value T sub C. So we're going to talk about that in just a minute. How do we find critical T values using the z-distribution? We're then going to find the margin of error. And the margin of error looks very similar to the one that it did for the Z, except for we're going to use T critical instead of Z critical, and we're going to use S as opposed to sigma. We then create left and right endpoints. My left endpoint is going to be X bar minus E. My right endpoint is going to be X bar plus E. And then I write my answer as left endpoint, right endpoint, in parentheses. When we're done, we compute that just like we did with hypothesis testing. We need to write a statement that explains what we have and what we see. So we'll write something that looks kind of like this. We are XX% confident that the true value of the population mean falls between this value and that value. So we take our confidence and we put it in context of So let's talk a little bit about how we find those critical t-values. So if I want to determine a critical t-value for a confidence interval, I'm going to take the confidence level in area, just like we did earlier, not percentage, subtract it from 1, divide it by 2. That's going to give me my alpha value, which my alpha value is the number that shows up on the top. So I do that first couple of steps to find my alpha value. And those steps follow pretty much the same exact thing that we did when we did the Z1. So that gives me my alpha value, and then I find the corresponding t value associated with that degrees of freedom. So I take my sample size, I subtract 1. That's going to give me the degrees of freedom. So let's take a look at this. A 90% confidence level with a sample size of 12. Let's find that critical z value. So my area is 0.9, subtract it from 1, gives me 0.01 divided by 2. That gives me 0.05. So that's my alpha value I need. Now, because I'm dealing with a series of curves, I need to find that degrees of freedom value. Our degrees of freedom is n minus 1. My sample size is 12. So my degrees of freedom will be 12 minus 1. My degrees of freedom will be 11. So I'm going to go to that corresponding row in the table. New degrees of freedom equals 11 on the left-hand side. And to the column corresponding to alpha equals 0.05. So I come up here. Alpha equals 0.05. That's the second column here. Degrees of freedom equals 11. So I come down here and my critical t value is going to be 1.796. And that's how we do that, find critical t values using the distribution right there. So we'll do another one. 95% confidence level with the sample size of 20. I need to find that area between 0.95 subtracted from 1, 0.05 divided by 2, 0.025. Degrees of freedom is n minus 1. 20 minus 1 is 19. So I'm going to go to the corresponding row in the t table, 19 degrees of freedom, column corresponding to 0.025. 0.025, that's that third column. Come down here to 19 degrees of freedom. My critical t value is 2.09. Sorry about that, 2.093. That's exactly what we got right here. Questions on this? All right, walk me through this one. How do I find the critical t value for 80% confidence level with the sample size of 8?
.8 minus 1.
0.8, that's area between. We subtract that from 1. That gives us 0.2. Then what do I do?
Divided by 2.
I'm going to divide that by 2. That's going to give me 0.1. Now what do I do?
So that's your alpha value. Then you find the degree of freedom, which is going to be 8 minus 1. 8 minus 1.
8 minus 1. So my degrees of freedom is 7. Alpha is 0.1. So we're going to come up here. Hey, Chris, man, tell me which one it is.
1.415.
Alpha equals 0.01. That's that first column.
So 1.415.
That's right. Degrees of freedom is 7. 1.415. So my critical t value will be 1.415. Very good, very good. So here's the other thing I wanted to show. So this last example says find a 90% confidence level with a sample size of 18. So if I take a look at this t-value chart, and they're almost all designed just like this, is at the very bottom, it's got this little infinite degrees of freedom. These are the critical z values that we saw earlier, right? We had 1.282 for 80. We had 1.645 for 90. We had 1.96 for 95. So all those critical values are down here. And as we see, as our degrees of freedom get larger, our value starts approaching that note. Gets closer and closer and closer. So the larger our sample size, the smaller my critical t-value will be. Right? As I go down this chart, as my sample size gets bigger, my number gets smaller and smaller until it approaches that critical value that we see. So here's the question. I have a 90% confidence level with a sample size of 12. We found that critical t-value to be 1.796. Will my critical t-value for this last example here, with a sample size of 18, will my critical t-value be smaller or larger than that first one we found?
It's going to be larger, right?
It will not be larger. As my sample size increases, my critical t-value decreases. So my sample size went from 12 to 18.
That's right. Mm-hmm.
Therefore, this is going to go from 1.796 to something, and we're going to find out what that is. So 90% confidence level, I find that alpha value the same way, still 0.05. Right, my degrees of freedom is now equal to 18 minus 1, which is equal to 17. So now we're going to come back. We're going to take a look here. Degrees of freedom is 17. I'm looking at the second column, 0.05. 1.74 is my critical value. 1.74. So my critical t-value here, 1.74. And if we compare that to what we saw up at the top there, 1.796, 1.74. As my sample size increases, my critical t-value will decrease. Questions on finding critical t-values?
Yeah, if we compare that to 95%, the critical t-value is higher, correct?
Correct. So
and at the sample size of 20.
That's correct. That is at a constant confidence level. So if I maintain the same confidence level, which basically means that if it's a 90% confidence interval, then a larger sample size will give me a smaller critical t-value. Now, increasing the confidence is always going to increase that critical value. As we see, if we go across, as my confidence level increases, so does my critical t-value. But if I go straight down, keeping that confidence level equal, as my sample size increases, my critical t-value decreases. So my apologies, it wasn't a blanket, not a blanket sample size. At a constant confidence level, increasing my sample size will decrease my critical t-value. Other questions?
You just said as the sample size increase, You said critical T decrease?
Critical t-value will decrease at a constant confidence level.
Got it.
Other questions about this? I know a couple of you were paying attention. That's good. For those of you that weren't paying attention, you should really make sure you know how to do this for your final exam, because there's at least 2 or 3 questions on critical t-values on your final exam.
So is the exam just accumulation of everything, or is it going to be based off on the last week or on the last weeks of this section?
Your final exam is mostly, I think it's like 95% new stuff, or stuff that we've learned since the midterm. So some of that stuff we learned early on, you're not going to be too concerned with. But there is always a little bit of overlap with anything, but it's mostly over the new material.
Okay, thank you.
No problem. So let's talk about hypothesis testing using the t-distribution. So if we're doing hypothesis testing for the t-distribution, not much changes. We still run the process the exact same. The only thing that really changes is how we find that p-value using the table. So if we're going to run a t-test, a hypothesis test using the t-distribution, here's what we'll see, right? We need to validate that the t-distribution is the correct distribution to use. And we do that by verifying that sigma is unknown, samples random, population is either normally distributed, and we only know S, our sample size may be on the small side. Those are the things that are going to trigger us to think we should probably deal with the t-distribution. I'm going to state my hypotheses, null and alternative, just like I did earlier. That doesn't change. I'm going to specify alpha. That doesn't change. I'm then going to find my standardized test statistic T, which the only thing that changes here is that instead of using sigma, I'm using S, because that's my best guess. T equals X bar minus mu over S over the square root of N. And then I find the p-value, noting that the degrees of freedom is N minus 1. So, finding the p-value stays the same. Left-tailed test, area under the curve to the left. Right-tailed test, area under the curve to the right. Two-tailed test, area under the curve to the left and right. We use the decision rule, and then we write a statement to interpret the problem. So here's an example of what we might see. Doritos claims their big bags contain at least 8 ounces of chips. Those that were in tutoring, this sounds very familiar. We sample 8 bags of Doritos, and we find the average weight to be 7.6 ounces with a standard deviation of 1.2 ounces. If we can assume the bags are filled with a process that follows a normal distribution, do we have evidence at the alpha equals 0.05 level that Doritos is underfilling their bags? All right, so I know nothing about Doritos population standard deviation, but their bags say they contain at least 8 ounces of chips. We think that we're not getting 8 ounces of chips. So we're doing this. We do not know sigma. We're going to write our hypotheses first because that's always the same process every time. So they claim that it contains at least 8 ounces of chips. The null hypothesis is mu is greater than or equal to 8 ounces. And the alternative will be the complement of that, which is mu is less than 8 ounces. All right, alpha is equal to 0.05. I don't know sigma. I've got a smaller sample size. We're going to assume it follows an approximately normal distribution. If I just don't have any outliers and my data looks okay, doesn't look any wacky, no wackiness about it, I'm probably safe enough to assume a t-distribution. So we're going to create a t-statistic based on that. X bar minus mu over S over the square root of n. 7.6 is my sample mean. Subtract 8 divided by 1.2 over the square root of 20. That's going to give me a t-value of negative 1.49. So this is a left-tailed test. I want to find the area to the left under that t-curve. It's going to be 0.076. Now, you're not allowed to have software. Software will tell you that this is what the answer is on your exam. If you have a question like this on your exam, here's how you would go about doing it. And this is actually how I learned how to do it. My t-value was 1.49. I'd come over here to my distribution, and I try and find 1.49 with the appropriate degrees of freedom. So my degrees of freedom in this problem, I had a sample size of 20. 20 minus 1 is 19. So I had 19 degrees of freedom in a t-value of 1.49. So I come here, I come down to 19 degrees of freedom, and I try and find 1.49 on the chart. Guess what? It's not going to be on this chart. Almost assuredly, this only gives you one value. So I take a look here, 19, I got 1.328, 1.729. Well, it falls somewhere in between these two values. So it's somewhere between 0.1 and 0.05. That's all I know from this chart. That p-value is somewhere between 0.1 and 0.05. So if I know it's somewhere between 0.1 and 0.05, here's what I used to have to write back in the day. 0.05 is less than our p-value, is less than 0.1. So the p-value falls somewhere between 0.05 and 0.1, and it doesn't equal either of those. The true p-value is 0.076, which is somewhere in between those two values. But if I know that my p-value is larger than 0.05, I'm going to reject the null. So since our p-value is 0.076, it's greater than our significance level of alpha, so we fail to reject the null and state that we cannot say the average Dorito bag contains less than 8 ounces of chips. Questions on that?
Yes, one quick question.
Yep.
For the p-value, is there, let me see, where it says p-value, how would you know how to write it with the t less than 1.49?
Oh, this right here?
Yes.
Okay, so that just comes from whether it's a left-tailed, right-tailed, or two-tailed test. So because I'm dealing with a left-tailed test, I want to find the area under the curve to the left of t. So the area under the curve to the left will be less than that value. So I get t is less than 1.49. When I looked up this value right here, I wasn't overly concerned, right? Because this doesn't have any negative numbers on it. It only has positive numbers on it. And that's because the t distribution is symmetric. So the area to the right of positive t is the same as the area to the left of negative t. So I just had to find that positive value right there, t equals 1.49, find the area to the right. And that's what we get that.
If the null up top is u greater or equal to 8 ounces, is it safe to say when you do the p-value, is it the opposite, or it could get tricky that way?
So it would be the opposite. It would be the probability that t would be greater than a number when we'd find the area to the right, which is exactly what this tells us, this chart right here. So we'll see How about this? Let's just copy this over. Make a new slide of it. I'll just put this up here. So if my hypotheses were backwards from what we just did in the example there. So at this situation, I have a right tail test. That's what that tells me right there. So my p-value is found by finding the area to the right. So let's pull it up on the board. That might be an easier way for us to take a look at this. If I have some kind of distribution right here that looks like this, if I want to find the area to the left, and I have some t-value right here, all of these numbers over here are small. So the area to the left is equal to the probability that my t-value is less than whatever my t-star value is. If I want to find over here the area to the right of some t-star value, well, every value over here is larger than t-star. So area to the right is the probability that t is, so I've got these, got that backwards there. T is greater than t-star. Area to the left, probability that t is less than t-star. Area to the right, probability that t is greater than t-star. So that's the notation. These are both just the p-values that we've been computing all of. Just written in a slightly different way. Does that answer your question, Quentin?
Yes.
All right. So let's take a look at one more example here. My favorite example, of course, we buy a 12-pack of soda, measure the fill volume of each bottle, and find the average fill volume to be 12.3 fluid ounces with a standard deviation of 0.5 fluid ounces. If we can assume the fill process follows a normal distribution, can we assume the fill volume differs from the 12 fluid ounces stated on the bottles? So we're trying to figure out whether it differs from the 12 fluid ounces stated on the bottles. So my hypotheses will be that mu is equal to 12 versus mu is not equal to 12. All right, I don't know sigma, so I'm going to end up using a t distribution here. So I compute my t statistic. My sample mean was 12.3. The null hypothesized mean was 12. S is 0.5, N is 12. I compute that t statistic, and I get 2.078. So 2.078, my degrees of freedom is 12 minus 1, which is equal to 11. If I use software, it's easy for me to find a p-value. The p-value is 0.061. Let's go look it up on the table and see what we have if we didn't have software. Degrees of freedom is 11. T is 2.078. So degrees of freedom is 11. I'm trying to find 2.078. It's somewhere between 0.05 and 0.025. So somewhere between 0.05 and 0.025. And the interesting thing here is that we're actually looking at a two-tailed test. So we basically need to double that p-value that we found. So instead of being between 0.025 and 0.05, it's going to be between 0.05 and 0.1. So my p-value is going to be somewhere between here. It turns out it's 0.061. So since our p-value is somewhere between there, we're going to assume we didn't have it in the problem. We're going to assume alpha equals 0.05 if we're not given it. Since our p-value is larger than 0.05, we fail to reject the null, and we cannot conclude that the mean field volume differs in 12 fluid ounces. Questions about that?
Yeah, so since we didn't see the p-value, we always assume that's going to be 0.05.
Yes, if you're not given a p-value in a problem, just assume it's 0.05. All right. So finding critical values for the t distribution. Finding critical t values for hypothesis testing. So we found some critical t values for confidence intervals. Now we're going to talk about finding critical t values for hypothesis testing. So if you remember, we found critical z values for hypothesis testing last week. Now we're going to talk about critical t values. So first thing I need to do is specify alpha and the degrees of freedom that I have. So I need to know alpha and I need to know the degrees of freedom. I need to know whether I'm running a left-tailed, right-tailed, or two-tailed test. And then here's how I will find the critical t-value. If it's a left-tailed test, I find the t-value that corresponds to an area of alpha, and I make it negative. For a right-tailed test, I find the t-value that corresponds to an area of alpha, and for a two-tailed test, I find the t-value that corresponds to alpha over 2, and I used a positive and negative version of that. So let's take a look here. For the hypotheses H naught, mu is greater than or equal to k, and HA, mu is less than k, find the rejection region if we want to set alpha equal to 0.05 and n equal to 21. All right, so I look at my hypotheses, and I have a left-tailed test. So to find a left-tailed critical t-value, I find the t-value that corresponds to an area of alpha and make it negative. So alpha is 0.05, n is 21. So alpha 0.05, degrees of freedom is n minus 1. Degrees of freedom is 20. So I need to go look up 20 degrees of freedom with an alpha of 0.05. Degrees of freedom equals 20. Alpha equals 0.05. Critical t-value 1.725. So it's 1.725. That's the number. But because it's a left-tailed, I make it negative. So the critical t-value will be negative 1.725. If it's a right-tailed test, I do the same process, except I don't have to make it negative because the table is already telling me that value. So if I have a right-tailed test, mu is less than or equal to k versus mu is greater than k, we find the rejection region by setting alpha equal to 0.1 and n equal to 28. So alpha is 0.1, that's the column I'm going to use. N is equal to 28, that corresponds to a degrees of freedom of 27. So I go to my t-table to the 27 row, and the alpha equals 0.1. So down here to 27, alpha equals 0.1, that's that first column, 1.314. So my critical t-value will be 1.314. And I don't have to change it. That's just what it is. So my critical t-value is 1.31. Now, when I'm dealing with a two-tailed test, I have to actually find alpha over 2, then look up the value on the table, and then make it the positive and negative version of that value. So if I have a two-tailed test, mu equals k versus mu is not equal to k, alpha equals 0.01, and n equals 10. So first thing I have to do, since it's two-tailed, take alpha divided by 2, 0.005. So my alpha that I'm looking up is 0.005. Degrees of freedom, n minus 1. 10 minus 1 is equal to 9. So I have 9 degrees of freedom. So 9 degrees of freedom, alpha equals 0.005. Come over here. 0.005, that's this column over here. And I come down to degrees of freedom equal to 9. And I get a critical t-value of 3.25. So my critical t-value is 3.25. Since it's a two-tailed, I actually have 2 critical t-values. Where were we? Right here. 2 critical t-values. Negative 3.25 and positive 3.25. I found that value on the table. I made it positive and negative because I need to have 2 critical values for a two-tailed test. Questions on finding these critical t-values using the table? All right. So following hypothesis testing procedures, everything just about stays the same as they did with the z-distribution, except for we're using a slightly different table and we've modified the t statistic just barely. But just like we did with the z-distribution, I can use those critical values that we found for the t-distribution, and then I can define my rejection region and use that rejection region rule just as we followed. So I'm just going to walk through this. You should have all seen it. We've done a couple of examples. We verify t-distribution is the right distribution. We state the hypotheses. We specify alpha, identify the degrees of freedom. We then determine the critical values, find the rejection region, compute t, and determine whether or not to reject or fail to reject based on where t falls in respect to that critical value. So, a couple of things regarding the t distribution. As far as your exam goes, it is going to show up a reasonable amount on your final exam. The things that you're going to want to be sure to know are how to find those critical t-values. Need to know how to find those critical t-values. We need to know what are the key things that they must know in order to use the t-distribution, or the things that we don't need to know to find the t-distribution. So basically, we just need to understand what those assumptions are. We need to understand how we, our t-distribution, our t-tail, our critical t-values change as our sample size changes. One thing you're probably not going to have to do, just because you likely need software to get a regular answer as opposed to kind of doing the little approximation method here that I used, is you're probably not going to need to find a p-value from the t-distribution on your exam, but you might need it for your homework. So make sure we went over it so you see that. But for your exam, I really want to make sure you understand what are the assumptions we need for the t-distribution and how to find those critical t-values. All right. Other tidbits to know. So I went through some of your assignments. I went through a couple of things, and I just saw some interesting things that you needed to know. So we're going to talk a little bit about it. So the percentage of variance explained by a treatment effect is denoted by R squared, which is another way that we can measure the effect size. This definitely shows up in your Cengage, and it even shows up on your knowledge check somewhere right here. I'm just going to, you know what, we're just going to keep going. So we can compute R squared based on the test statistic T and the degrees of freedom. So R squared is equal to T squared divided by T squared plus the degrees of freedom. So for example, if I have a sample of n equals 16 scores that produces a T statistic of 2, what's the value of R squared? So if I want to find R squared here, I need to know T, and I need to know my degrees of freedom. T is equal to 2, so I get 2 squared divided by 2 squared plus my degrees of freedom. What's my degrees of freedom going to be?
15.
15. So I get 2 squared, which is 4, divided by 2 squared, which is 4 plus 15. That's equal to 4 over 19. And 4 over 19 is, whatever 4 over 19 is, 0.21.
Where did 15 just come from?
Say that again?
Where did 15 come from?
15, that is the number of degrees of freedom, which is found by taking n minus 1.
Okay.
Questions on finding this? Problem like this might potentially show up on your knowledge check. So that's how we would do a problem like that. Other things to know. The sample variance can be found using the equation as follows. S squared is equal to SS divided by the degrees of freedom, where the degrees of freedom is n minus 1. The estimated standard error is found using the following equation. S sub m is equal to S divided by the square root of n. So what is the sample variance and estimated standard error for a sample of n equals 9 scores with an SS of 72? All right, so I want to find the sample variance and the estimated standard error. Well, here is the equation for my sample variance, S squared. It says take SS divided by the degrees of freedom. What's my degrees of freedom?
8.
It's 8. So SS is 72. Degrees of freedom is 8. My sample variance is 9. If my sample variance is 9, what's my sample standard deviation?
24.
Not 24.
Would you just square root 9?
Just square root 9. It's 3.
81.
My sample standard deviation is 3, right? Because the standard deviation is just the square root of the variance. All right, so that is S. Now I can find, because it asks for the estimated standard error. Estimated standard error is S over the square root of n. S is equal to 3. The square roots of n, that's the square root of 9. 3 over the square root of 9. What's the square root of 9?
3.
3. 3 over 3, which is equal to 1. So my sample variance is 3, or sorry, sample variance is 9. Sample standard deviation is 3. Standard error of the mean is 1. So this problem also definitely shows up on your knowledge checks. Questions about that? All right. Some more conceptual questions. Suppose we have a standard deviation of 10. What will our standard error be of the mean if our sample size is as follows? N equals 1, n equals 4, n equals 8. So what's the equation that we have to find the standard error of the mean?
Standard deviation over square root of n.
Standard deviation of the square root of n. We just used it, right? So if I want to find the standard error, I take the standard deviation divided by the square root of n. Standard deviation is 10. I'm going to divide it by the square roots of n. N is equal to 1. 10 over the square root of 1 is equal to 10. If I take a sample of size 1, the standard error and the standard deviation will be the exact same thing. Let's let n equal 4. Same process. Instead of n equals 1, n is now equal to 4. The square root of 4 is just 2. Standard deviation is, sorry, standard error is 5. If I let my sample size equal 8, I just change n to 8. Goodness gracious, I don't know what the square root of 8 is off the top of my head. Square root of 8 is 2.828. And then I plug that into my calculator and see what I get. I get 3.5, approximately 3.5. So, what is this example supposed to show us right here? One, we need to know how to find the standard error of the mean if we're given a standard deviation and a sample size. Second, as our sample size increases, our standard error will decrease. As sample size increases, standard error decreases. But it's not a linear decrease. What that means is, if we take a look, I'm dividing by the square root of n. So it's going to decrease at a rate of the square root of n. which means this. I went from n equals 1 to n equals 4. I multiplied my sample size by 4. 1 times 4 gives me 4. But I didn't divide my standard error by 4. It only divided by 2. When I doubled it from n equals 4 to n equals 8, I multiplied my sample size by 2, but I did not divide my standard error by 2. So it is not a direct relationship between those two values. Questions on that? All right. The central limit theorem states that as my sample size increases, which of the following will happen? So, do we remember what the central limit theorem is?
I think sample mean approaches the population.
I think it says as the sample size increases, the sample mean approaches the population mean.
So, I mean, this isn't really a multiple choice question. This is more of like a true false question for each one of these. So, first off, we need to know what the central limit theorem is. Do we know what the central limit theorem is?
It's something to do with inferential statistics, I believe.
It sure is. It sure is. All right. I don't know what's going on with a lot of stuff. I'm not mad. I'm not blaming you for any of this. Central limit theorem used to be a big focus when we would teach statistics because it's the most important thing in the world when it comes to statistics. That central limit, most powerful rule. So the central limit theorem states basically this: as my sample size gets larger, increases, the distribution of the sample mean becomes approximately normal. So as my sample size gets bigger, the distribution of my sample mean becomes approximately normal, which is crazy. Doesn't matter what the distribution is that we sample from, as long as we're looking at the mean and my sample size is large enough, that distribution will be approximately normal. So that's what the central limit theorem states. And it goes along with what we call the law of large numbers. So the law of large numbers states that as my sample size increases, my sample mean will approach my population mean. My sample standard deviation will approach my population standard deviation. So basically the sample will approach the population as our sample size gets larger, which should make sense. So that's what the central limit theorem is. So let's come back. Let's answer these questions. So the central limit theorem states that as my sample size increases, which of the following will happen? Will the sample mean have an approximately normal distribution? Yes or no?
Yes.
Yes, it will. That's pretty much exactly what the central limit theorem states. If my sample size increases, will my standard error increase? Yes or no?
No.
Oh,
No.
No. Right? We just showed right here that as my sample size increases, my standard error decreases. If my sample size increases, will the sample mean approach the population mean? Yes or no?
Yes.
Yes, it will. So let's make sure we know those things. A couple other questions, things we might want to know. A researcher conducts a hypothesis test from a sample with an unknown population variance. All right, that first line, what do I think I should be thinking about at this point?
T-distribution.
T-distribution, right? I just heard unknown population variance. That should be springing in my ears, T-distribution, T-distribution. If the degree of freedom is 25, the sample mean is 30, and the sample variance is 5, what is the sample size? What's the answer?
26.
26. How'd you get that, Perez?
Because the degree of freedom is the sample size minus 1.
Degrees of freedom is n minus 1. And if n minus 1 equals 25, then n must equal 26. So, understand that it works both ways. If I give you a sample size, you find degrees of freedom by taking n minus 1. If I give you a degrees of freedom and ask you to find the sample size, I just need to add 1 to the degrees of freedom to get sample size. So, while we have that degrees of freedom is equal to n minus 1, if I want to work backwards, n is equal to the degrees of freedom plus 1. All right. If I run a hypothesis test at alpha equals 0.05, what will happen to my critical t-value as my sample size increases? Will it remain the same, decrease, or increase?
Decrease.
It will decrease. Right, we talked about this earlier. If I run it at alpha equals 0.05, constant alpha value, I'm increasing my sample size, so my critical t-value will decrease, right? Constant alpha, sample size gets larger, decreasing critical t-value. Very good. What things will impact the width of a confidence interval? So we didn't talk a lot about this, but let's pull it up. So I'm going to pull up some information here about the confidence interval. So here is basically how we compute a confidence interval. We have the margin of error. We take the sample mean, we subtract it, we take the sample mean, we add the margin of error, and then we see what we get. A lot of times what we do is we just write it like this. X bar plus or minus T critical times S over the square root of it. So if I take a look at this and try and figure out what things will impact the width of a confidence interval. So things that impact the width all comes from the plus and the minus. All comes from the margin of error. So if I say what things will impact the width of a confidence interval, I just need to take a look at this right here. So the things that will impact the width would be sample size. As my sample size gets larger, this number gets smaller. So if my sample size changes, my width will change. my critical t value. My critical t value has an impact here, but really, the things that impact the critical t value are sample size and confidence level. So it's the t critical value impacts it greatly, but the t critical value is based on sample size and confidence level. So those are the two key things: sample size, confidence level. Technically, sample standard deviation slash variance can impact the width, but that's not really something that we can change or we can control. But technically, sample standard deviation and variance. So the key things I want you to know that impact the width of a confidence interval: sample size, confidence level, and sample standard deviation slash variance. The sample mean doesn't matter what it is. If I change it, the width doesn't change because the width is based on the plus or minus. For example, if I have 8 plus or minus 3, my confidence interval would be 5 to 11, and the width of that would be 6 units. If I were to make it 100 plus or minus 3, well, then I'd be from 97 to 103. Still has a width of 6. So the only thing that can change the width is changing the plus or minus section, which is T critical times S over the square root of it. Questions on some of these things that you should know?
Class is killing me.
This class is killing you?
Just a little bit.
That's okay. It's killing me too, man.
Professor,
Yeah.
can we have like the slides of the class, like this one you've solved the questions unsolved? You know, the one you sent, the questions were not solved. So can we also have this one? I mean, the one you solved the questions during class?
Sure. Sure. I'll save this copy here and then send it to you. All right. Attendance, if I call your name, it means I don't have you. Eric, Martha, and Azina. All right. So that's the attendance right there. Let me verify that I didn't miss anything. Aubrey, yes, I got you, don't worry. With that review of things that I want to make sure that you know for your exam from this section, make sure we know how to find the standard error.
Will we have time in class before our final to go over as a class the study guide?
Maybe. You mean like on the final exam day?
Well, I know that you had changed your tutoring to Tuesdays, but I have another class on Tuesdays. So I didn't know if on, I don't know, any one of our Saturdays that we have for class that we would have time to go over that. just to see, you know, if we're doing things in the right orders.
Sure.
Yeah.
So let's see where we get next week. How long class takes. We have time at the end of class. We'll deal with it then. Otherwise, I'll hold an extra tutoring session on that week before your final exam. And then we can talk about anything you need for that. So we'll find time for it before your exam, I promise.
Okay, thanks.
No problem. All right, just double check and make sure I'm not forgetting anything. We need to know the assumptions behind the T distribution when we use it. We need to know how degrees of freedom and sample size are related. We need to know that as my degrees of freedom increases, how does that change my critical T value? We need to know the things that affect the width of a confidence interval. We need to know how to find critical T values. And that looks like it's it for this section. Questions for me?